In the last part of the lecture, we're going to see some more applications of Taylor's remainder. So specifically, we're going to see how to apply Taylor's remainder to evaluate the error of approximation, right? So if we have a function f that equals the sum of its Taylor series, or actually even if it does not equal the sum of its Taylor series, but still we want to approximate our function with Taylor's polynomial, right? So the error of approximation is Taylor's remainder. So, and we can actually use this Lagrange's form of the error to figure out how good the approximation is. So here is an example. So estimate the error when T4 is used to estimate uh, square root of E. All right. So the idea here is that um, e to the x is 1 plus x squared over 2 factorial plus x cube over 3 factorial plus x to the 4 over 4 factorial plus and so on, right? So this part is our T4. And the question is, so basically, how good is this? If we, instead of computing e to the 0.5, which, by the way, we cannot really compute it like exactly, because when we do it on a computer, under the hood, the computer probably just computes the sum of the Taylor series, right? So, and the question is how good this approximation. So the error term here. Um, so we know that our e to x minus this t4 of x is going to be well um, nth derivative evaluated at sorry yeah sorry n plus first derivative evaluated at c over n plus 1 um, factorial divided by x to the n plus 1. Yeah, and in our case x is 0.5. So further, so my all consecutive derivatives of the exponential function are just e to the x itself. All right, so it's going to be like e to the c. So, and this is going to be 0.5. All right, now just exactly how small is this? Well, basically, so notice that here we have e to the c, and the whole idea of estimating our exponential function with a power series is that to sort of get rid of e to the x, because the idea is that e to the x itself is probably hard to compute, right? So we shouldn't have e to the c even in the error estimation. So then how small is it exactly? So this is going to be smaller than what? Well, so how can we estimate e to the c? So we know that e is something like 2.7, right? Um, it, so this is definitely smaller than e to the 0.5, because c is between 0 and x, and our x is 0.5, right? But how can we roughly, I mean, we know that e is smaller than say 3. I mean, e is 2.7 something, so it is definitely smaller than 3. So we could write that this is smaller than 3 raised to the power 0.5. But this is square root 3, and it's probably better to work with integers, right? So this is even smaller than 4 raised to the power 0.5, which is just 2, right? So our error term is in fact smaller than 2 times 0.5 raised to the power, well, n is 4, right? So to the 5 divided by um, n plus 1 is really n is 4, so this is 5. factorial is 5 factorial, and this is 120, I believe. Okay, so this is the error. I mean, you can compute it, of course, but I think the point is clear, right? So this is how we can estimate the error. So how can, I mean, if we compute the square root of e using just the the Taylor polynomial of degree 4, so how good is it going to be of an approximation? And it turns out that it is pretty well decent in the sense that um, the error is 0.000 something, so I guess at least three decimal places are going to be correct. All right, so another type of a problem is sort of a reverse problem. So um, if we want to approximate our function with the sum of its Taylor series to get a reasonable accuracy, so just how many terms do we need to take? And here is an example, right? So if we want to approximate e, right? So just e to the 1, e to the 1, which is, just 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus and so on. So if we want to compute a certain number of decimal places of the number e, um, so how many, so what should be the order of the Taylor polynomial if we want to just, chop off our the whole power series and just take some finite part of the power series? So just how many terms do we need to take? Right? And here the basically what we're going to do the same thing, right? So the remainder e x minus tn of x should be really e to the power c times n plus 1 factorial times x to the power n plus 1. In our case, x is just 1, right? So x is just 1 because we are approximating e, which is e to the 1. Right, so this is really e to the c divided by n plus 1 factorial. And again, so c is a number between 0 and 1, right? Um, Now we don't know what the number is actually, but we do know that it is between 0 and 1. So which means that the error is definitely less than e to the power 1 divided by n plus 1 factorial. And again, um, so e itself, I mean, it doesn't really make sense to plug in e into this equation just in order to be able to find the error of approximating e itself, right? So because the idea is that we pretend that we don't know what e equals, right? So but we probably do know that e is less than say 3. So this is going to be less than 3 over n plus 1 factorial, right? And if 3 divided by n plus 1 factorial is less than 10 to the minus 5, then we are done. So let us try to find n from this inequality. So flipping it over, we will get n plus 1 factorial over 3 is bigger than 10 to the 5. Right? So n plus 1 factorial should be bigger than 300,000, I believe. Yeah. Because this is 3 times 10 to the 5. So it remains to find the number n such that n plus 1 factorial is bigger than 300,000. And here we can just do trial and error because factorials they grow very quickly. So 6 factorial is 720. Then this is going to be, say, 7 factorial is bigger, 8 factorial bigger but still not enough, and 9 factorial is bigger than 300,000, right? So 9 factorial is already enough, right? So this is 9 factorial. So which means that n plus 1 equals 9 and n equals 8. And this is the answer. So it is enough to find 8 terms of the Taylor series. And if we approximate e to the x with the Taylor polynomial of degree of order 8, then this is going to be enough to find e with the error at most 10 to the minus 5. All right, so here is the printed solution, and that's basically it, and that's the end of this part and the end of the lecture.